Samantha,
Oh, me.
will you read first, please?
The statement of all circles are similar may seem intuitively obvious. Since all circles have the same shape, even though they may be different sizes. However, we can learn a lot about the properties of circles by working on the proof of this statement. Remember that the definition of similarity requires us to find a sequence of dilations and rigid motion transformations that superimposes one figure onto the other. Zach is describing the
Swan.
That person has three different names
He
now.
would prove that circle A is similar to circle B. Zach translate circle A until its center point.
You got this, Sam.
Coincide with the center of circle B, then enlarge circle A by dilation until the points on circle A coincide with the points on circle B. Or you would shrink circle B by dilation until the points on circle B coincide with the points on circle A.
So he's saying you move this direction. Okay, you move it this direction until the points coincide. And then you would dilate it to make it larger until their circumferences
There we go.
land on each other. Yeah, wow.
It's been a long day already.
Amen, brother.
Guys,
Okay.
I just went halfway through.
We had devil
Oh,
presses
yeah.
this morning, so.
It's actually gone pretty fast.
It's Wednesday, my dudes.
I didn't get to
Ah!
this morning.
You didn't what?
I didn't get to hear announcements this morning
Mm.
because choir.
Oh, yeah.
is practicing before
Yeah,
school.
we were watching
'Kay.
Ratatouille in here. but-
So,
Wow.
as we look at this, Sion has some questions. She says, after the translation, what's the scale factor for the enlargement that the circle carries circle A onto circle B? And what's the reduction for circle B to circle A? How would you answer her questions? Scale factor. What did we do up here? How did we determine the scale factor?
We counted.
We counted, but what was the thing that we determined? So this one we counted 4 and 8.
We determined the ratio of corresponding sides.
The ratio of corresponding sides. So in order to say that the scale factor was 2 right here, we went ahead and said, okay, what is 8 divided by 4, right? So we took the larger one, and divided it by the smaller one. That was the scale factor to enlarge. So what are the things that we could talk about in these circles? There are no numbers.
Well, there's R1 and R2.
There's R1 and R2. So how could we say what is the enlargement factor for circle A to be superimposed onto circle B?
So it'd be R1 over or
It was
R2.
double.
Be the other way. R2
R2
divided by R1. Now, this is not saying 1R and 2R. Those are actually labels. They just, I guess, didn't know how to work the subtext button on Microsoft Word. So this is actually R1 and this is actually R2. They're mad goofing. So, to enlarge, we would say the larger one divided by the smaller one. That's our enlargement factor. Okay?
Oh, it says enlargement. I was like, what in the
Yeah, it
world
looks
is
like
that
that.
word?
Yeah,
Enlarge.
enlargement factor.
Enlargement.
So you would multiply whatever this is by the smaller portion of circle A. Okay? How about the scale factor for reduction or the reduction factor?
That'd be R1 this time over R2.
Exactly. Very nice. So that would be the multiplier to make it smaller. Smart. So then, based on Zach and Sion's discussion, we're probably convinced that circle A and circle B are similar. But another way we might convince ourselves that the two circles are similar is to find the center of dilation that maps the pre-image point from circle A onto corresponding image points on circle B. How could we locate the center of dilation from circle A to circle B?
Pick 2 points.
Wait, how do we what?
Corresponding points.
How do we find the center of dilation? So like up here, what did we do to find the center of dilation?
Line.
You-
If I'm like D to D
Draw
to
the-
A.
Yeah, the corresponding points. That's what those are called, right? So we find corresponding points and draw lines through them. So if you notice right here, when I drew that arrow from A to B, I didn't just stop at A. Where did I take where did I take the rest of that line?
Under the line.
Yeah, to the other line on the bottom. What is interesting about points R and S? Did it say anything of note?
They're tangent to each other.
They're tangent to each other. So that means that they touch the circles at corresponding points as well. So if we're going through the center of corresponding circles and a tangent line that's at the same kind of spot on each of the corresponding circles, then the center of dilation is right where those intersect. Just there. I wonder if people on YouTube think like 7 different people teach this class.
Maybe.
Yeah.
Probably not.
It's not 7 different people. I'm just crazy. I'm out of my mind.
We know.
He's not.
I'm out of my mind.
Oxbow.
Okay, so there's the center of dilation. Yeah?
Yeah.
Do you see anything else interesting about this? These figures we've made right now? Yeah, Samantha. Ooh, it's a triangle. There are 2 triangles. Be nice, be nice. Anything else we might know about those triangles?
Very similar to each other.
Ooh, they look like they're similar to each other. They also appear like they are right angles. How do you think that we could know that they're similar to each other?
So, in circles, when you have that, the radius line,
Mm-hmm.
there's, I forget what equation it is, but it's always that line is at a like 90-degree angle
To what?
to the.
They have the
It's
same
like it's
angle.
there, but I
Yeah.
can't remember how to.
So
describe it.
the
You know what I'm
radius,
talking about,
yes,
right?
I do. The radius always meets a tangent line at a 90-degree angle.
That.
Okay, so that's just a true statement about circles and tangent lines. A radius of a circle will meet the tangent line. If it's at that point, it will meet that tangent line at a right angle. That's part of the definition of a tangent. Okay, so we know that those are both right angles. We also just determined that these are similar, right? There's a multiplying factor between those two. We know that this angle is just itself, and that's an angle of both of those triangles. We also should be able to say, okay, if this angle and this angle are the same, then that means this angle has to be the same as this angle, which means those triangles are similar.
Similar.
Huzzah!
Hey.
Okay, that's great news. That means that all of their sides are going to be ratios of one another, right? So, we located the center of dilation. Now what I want to see is to have us draw some chords, triangles, or other polygons that are inscribed in each circle that would be similar to each other. So we're going to draw one shape in our circle A, and we need a similar shape in circle B. Could I be like,
What about like an arc or something like that?
Draws a square.
Smiley face?
No, you can't do square.
are those similar?
Yeah.
Yeah.
Oh.
Well,
I don't know. How do you know? I don't know. Are they mathematically similar? Not our colloquial similar definition,
Alright.
right? But are they mathematically similar? Hadassah, yes.
Check the vocab on it.
I got one for you.
Hold up.
Okay, go for it. Yes.
I could be wrong with an arc.
An arc? Okay, which arc?
Alright, I think it's like the B. Like I don't know how to put this into words because math. So B, then boom, like
So like
or like this, like yeah, you
Kinda like
you know
here?
what I mean, yeah.
This arc?
Yes.
and this arc. So those arcs, yeah, those arcs are similar, right?
Could do a central angle that goes up from the like radius line.
Okay.
And so from the radius line of A, just go up on that. And then also from the radius line of B, and then following that, what's the word? The line of B, that way. You know what I'm saying?
Like this way?
Yeah.
Okay, so if I extended the line that I've already kind of drawn a little bit diagonally, is that what you're saying?
Yeah. They have similar central angles.
Ooh. So if I continue that line on, Hadassah is saying that this angle will be the same as that angle, right? Yeah. So what else could I say? William said that this and this, like this arc right here, those arcs are similar. And he's right. Okay. We could also draw a diameter. So like the diameter of this line that goes through, we know that if circles are similar, all of their corresponding parts are going to be similar as well. So diameters could work. Let's think about another chord or something though that we could draw that would also be similar. So like if I were to just draw this chord right here, is there a way that I could draw a chord in triangle A that would be the same or that would be similar? Jacob, what do you think?
Could you just keep extending it and it would soon go over? Or
So like keep extending it this way?
yeah,
I maybe, but I have no way of really knowing that.
that's what I was like.
Could you?
Yeah.
Could you use the line that you've drawn between point A and B and go from the like corner where those arcs meet and draw them?
Like this?
Sorta. Hold up, let me show.
Yeah, actually, no, yeah.
If you want them similar, like on the same side,
Mm-hmm.
like that.
Okay, so you said draw it from here to here and from here to here. They look similar, but how can I know that they're similar? Because this side is anchored, like this spot down there at the bottom is anchored to a point that I know. But this spot up here, I have no way of knowing if they're hitting at the same spot. Because it could be hitting at this spot or at this spot just as easily, and I wouldn't know. Right? So what's a way that I could... What?
The other way, like what you did before, where it was from the corner to the right angle that we have.
Okay.
That would work.
Yeah.
Because all
That's 2 points
angles
that we
work.
know.
That would work. Yeah, because that is 2 points that we know. Is there a way for me to create more points that I know?
No, that's not it. I was thinking a concentric circle, but
Yeah.
um,
Well, how did I get
this, what is it? A
No.
tricant. Yep. Second. Yeah.
Let me go back up here for just a second. Tayson, I see your hand, but I'm not quite ready to diverge from this just yet. How did I get all these lines here?
No, you want D,
Between points.
I did it between corresponding points, right? So I saw the corresponding points first, and then I created the center of dilation. But could I go the other direction too? Like if I knew the center of dilation and
Yeah.
a point, could I make other corresponding points to that point?
Yeah.
Yeah, so using that thought, if I come here and say, okay, I want to make a chord that's similar to this chord right here that I have in circle A, but I want to make one that's similar to it in circle B, then what I can do is I can use my center of dilation and a straight edge to say, I'm going to create another line that passes through both the points at the edge of the art or at the edge of the chord that I've created and my circles and the center of dilation. So I see that this hits in 2 spots, right? It hits here and here. I drew that chord to the second spot. So what I'm going to do is I'm going to use my straight edge again, and I'm going to draw this chord at those corresponding points.
It's almost like doing combining the. Well,
We got another triangle.
it's almost like combining the secant and
That is an
tangent
obtuse triangle.
kind of together because you're almost right on the edge, but also going through it.
Yeah, that's true. Yeah, and I'm using the properties of similarity and knowing where my center of dilation is to be able to create other shapes. Now, I heard someone say triangle just now.
My brain's being all 3D and it's hurting my head.
I could make a triangle by connecting these points that I have to another point. So like, let's say, what if I go from this point to this point? Now I've got a big triangle there, right? Do you see that here?
And you can make those similar by doing the same.
And I can make them similar by doing that same thing right here. So now I have two similar triangles. Now I could even do this, take it a step further and say, I'm going to make a quadrilateral by connecting these points as well. And these points. And I know that those two quadrilaterals will be similar because I'm basing the vertices off of points that are created from the center of dilation. Okay? So I know that all those shapes are similar because I have based them all in the circumference of the circle, why did I say it like that? And the center of dilation. Okay? And I know that they're corresponding points, so that means they must be similar. Tayson, did you have another thought?
Well, okay, so I started raising my hand way back when it's just like, hey, do you know two chords that would be similar? And mine wasn't just taking a single chord and mirroring it over. Mine was taking that line all the way through, and then the chord created by that singular line.
Oh, snap. He on a new level.
Alright.
So like if I were to do I don't know, let's just say I was to do like this one right here.
It's basically the same thing.
Bow.
Just how to describe it.
Yeah, this chord and this chord would be similar, right? Because it's just chords along that line.
Weird perspective angle of like a duck. Like if the duck got like really close to the camera and the duck, and then those were the outcomes. You know what I'm talking about? Images like that.
I do know what you're talking about, images like this.
You see it?
And actually this is like the basis of perspective in art too, right?
Yeah,
Is
it's
you
awful.
are trying to create similar figures from a foreground to a background or to a point of what's that called? Point of disappearance? Point of
Vanishing point?
vanishing point. Thank you. Wow, Tayson's in art class, you guys. Dang. Tayson, you're so artsy.
Different level. Why does that thing hold 3 pounds of lasagna?
Who doesn't?
Why would it not?
It's a lasagna.
I love 3 pounds of
Actually, no,
lasagna.
it's 6 pounds technically because there's 2 3-pound ones. But
Lasagna sounds really good, right?
The only thing that's better than 3 pounds of lasagna is 6 pounds of lasagna. Okay, anyway,
You know what pounds of lasagna? Spam casserole.
you would have to do a lot of convincing for that, and in order for that, I would need a taste test. So there's no argument you can make.
Tater tot casserole.
It's hard to
These things, okay, we are gonna keep working on math.
Tots,
and it's actually really good.
So here's the key right here. Did you draw those on your papers, first of all? Okay, great. So the thing that we need to do under question 3 is we need to explain how we know that they're similar. Now, I've said it a couple of times, so I want you guys to use your words to then also state it. What do you think? Don't give a darn what other people think. What do you think about that? We're going to be kicked off of YouTube for copyright infringement.
Yeah.
Mr. Ball, you're
We
averaging
don't
like
sing the
10
full
views.
song, we do it like a slight cover. So
Yeah, it's true. It's
fine.
like less than 20-second snippets and we're chilling. Okay, so what do you think? Somebody talk me through this. How do we know that the corresponding figures are similar?
Are you talking about like the circles or like the triangles or the...
The shapes that we drew in there.
The triangle.
So the triangles, they had
Because they
similar
have the same
angles.
angle.
Okay, what else were we talking about outside of the circles?
You got that
The
triangle on the big triangle on the top. That's in the circle. Another triangle there. We got a square in one of them.
We use it outside the circles.
Yeah, I know. I'm trying to.
We went from like the point of. My
Dilation.
yeah.
Yes.
Thank you.
We went from the center of dilation, right?
Center of dilation, and then we like drew the line.
Because of that center of dilation and using those corresponding intersections, that makes everything similar. Okay, so you need to write that down, okay?
Q-U-E-S-T-Y. That's how you spell center, right?
I'm gonna put S-I-N. Center?
Questy. That's how you spell center.
When did that remind me of
Yeah, it was
Yeah.
Mickey Mouse. It was Mickey Mouse. That was the only way I learned how to spell mouse.
Because melody is more powerful than words.
That's why studying with music helps.
Okay, so based on the figures that we drew in question 3, we need to write some proportionality statements that we know are true. So in order to do that, we need to name some points.
I named him David and David Prime.
Okay?
it?
Let's name this point right here David,
And David Prime. Yeah.
and then the corresponding point up here David Prime.
David.
Dude.
Okay? Now let's also name this point right here.
David Senior.
We're going to name it.
Senior David.
Oh, we already have an R. We're going to name it
David Senior.
L.
It's
And this one, M.
from Inside Out.
This one, N. And this one, O. LMNOPY QRSTUV NOP.
I've been trying to learn how to say.
Okay, so what are some, let's spit out some proportionality statements that we could make. Remember that proportionality statements, just like R2 over R1 was a proportionality statement, we need to make some other ones now. I'm also going to name this point P.
Oh,
The center of dilation is P.
Okay, would the segment David Prime be similar to RS?
David Prime should be similar to So that is a proportionality statement, yes. Or that is a ratio. Actually, that's a ratio. We now need to make a statement that completes this proportionality statement, because that's just one ratio. A statement has to be two ratios that we've claimed are equal.
P David
Equals.
PR.
P David PR. So he took this big section to this big section. I should not mark them like that. This big section to this big section. And he's saying that is similar to this big section over this big section. Smaller section, I mean. So P David over PR.
P Sherman will be wasted me.
God bless you. Okay. I've never done a deadlift PR.
Oh,
Yeah.
darn.
But y'all know Josh Potter?
Yes.
No. He was the same age as our first graduating class. He sent me a video yesterday of him bench pressing 315.
Does he do pottery for fun?
No, Dave does. That's my roommate. But Josh Potter
15.
checked up 315 on a bench. That is crazy.
Golly.
My max is 255. And I'm like a pretty large person.
How many circle things is that?
His was 3.
3 full plates.
3 full plates on each side.
Oh. That breaks.
Well, lightweight, yeah.
It's crazy. Okay,
255.
I need another one.
Gosh. Alrighty.
So we have to take segments from the larger and compare them to segments of the smaller.
BS and AR, you know.
Yeah. Oh, sorry.
So AR to BS, that's fine. It's just a name of a line. It's fine. Now, what is that? Let's complete that proportionality statement. So what part did we go? What order did we go in? Did we go large circle to small, or we went small to big, so now we need to go small to big
Can
again.
you zoom out a little? Just a tad. Thank you.
Hot dog, hot dog, hot dog.
Think about this.
Oh, but,
So AR to BS, now we need a different one that is similar to, or that is the same proportion.
BS
Let's
to
do
AR, anyway.
P David over PI.
P, Dave.
No, that is.
Yeah.
not.
Wait, P David to P what?
R.
No, because if we go from small, you went then again from small to small. So we went first. We went from small circle to big circle, but then we tried going from small circle to small circle, and that is not an
No,
accurate
we
one.
go PR to PS.
PR to PS would work. Okay. All right. Are there any questions on how we find these? Remember, if you are starting with a proportionality statement where you go small to large, you need to finish the proportionality statement from small to large. Okay? Great. Do 3 on your own. Okay?
I've never
So pick a line in the small circle divided by a line in the large circle, and then pick another one in the small divided by a line in the large circle.
In the small or like just
You can do various. I'm just saying you guys have to take it from a step of just like whatever is happening right now to being able to do it on your own. So think critically about this as we're going through it.
Are you saying more proportions?
would technically the PS to PR work like
Well, PR to PS would work, or PS to PR
That's what I
technically,
did.
but you'd be going big to small. so
yeah,
make
then
sure.
could I do the like P and then B or yeah. What?
PA to PB
Yeah,
is one.
PB to A.
But equal. Oh yeah, you can do.
PB to PA.
Yeah.
Yeah, PS over PRA would equal PB over PA.
That's what I was thinking. I was like, is that why PB the things work?
Nothing rhymes with boring.
Okay, any questions?
Boring.
If you have a question, you need to ask it to me.
Yeah, why does nothing rhyme with orange?
Ask me pertinent questions.
That's a B.
I'm right here. You can ask me questions. Here I am. Ask me.
That is very odd medicine.
Very creepy.
It is very creepy.
Do your work.
Ask me a question.
Shh.
That.
Shh. Look, this whole process isn't going to help you get better at math, so be quiet. Yes. Yeah, so then the only thing that you have to do is figure out another one that would go like between the two. So if you did PO, then you would have to do another one that's like corresponding. So if you did PO, you'd have to name this point. So which you can do and you should do. So if you do PO, what is that?
David?
That's David.
Yeah.
You pick a new name for it.
Oh, okay. Then this would be 8.
Okay, cool. So then if you go RS to AB, then you could go
P-O to
P-O.
P-H.
Yeah,
3
that
more.
would work. Jacob.
See if we can work.
Chase.
Okay.
Chase.
They're below the line.
Okay. Money. this one. So you went PM to PO. So that was small to big, right? But then here you went,
Small.
oh wait,
But I want s-
PM, PO, PO, yeah. Oh yeah, I misread that. Yeah, that's
Cause
good.
like, that's small.
Yeah, you're right.
Okay, that's good.
Okay. Also, as another hint, you could even think about these as like triangles. So, hint, these are two similar triangles, and we've dealt a lot with triangle similarity, so you could use that too.
Yo, one of the triangles is PBS. I just realized that.
Is that
PBS Kids.
Is that good water? Said the science kid anyway.
No.
Brought it from home. All right.
Wait.
Here's a proportionality statement that you may not have considered. The circumference of circle A divided by the diameter of circle A is equal to the circumference of circle B divided by the diameter of circle B. What is the formula for circumference?
Circumference pi times diameter. No.
Pi times diameter. What's another way we could call the diameter?
Pi 2r.
Yeah.
And then area
R
is.
squared.
Because remember that we only have the radius right now, right? So we could have 2 times r1. And over here, the circumference would be equal to pi times 2 r2. Okay? And then in the diameter down here, what's the diameter of circle A then in terms of r?
2r.
2r1. What's the diameter in terms of r2?
2r2.
Good.
R2d2.
I was
So-
thinking the same thing.
If I were to actually, here's the convincing that these are true. If I were to say, okay, it's the circumference, but then instead of saying it as the circumference and I say it as pi 2r1 and pi 2r2, check out what happens when I rewrite this proportionality statement.
What's the thing between those?
Equals. Sorry.
It looks like the not equal.
Gotcha. It is equal.
That-
Okay? And we're trying to say, is it equal? I need to be convinced that this is true. Well, what's 2 divided by 2? Right here.
That's 1.
Whoop.
Uno.
What's R1 divided by R1 right here?
That's 1.
Whoop. What do I have left? Pi. On the right-hand side, what's 2 divided by 2? Whoop. What's R2 divided by R2? Whoop.
So you have pi.
So what do I have left?
Pi equals pi.
That's a true statement. So that means that proportionality statement, I am so convinced that that is true. Nice.
I'll also have you know I've since named all other points to be alternates of David.
Sounds exhausting. Okay, since the ratio of the circumference to diameter of the circle is the same scale factor for all circles, we've named it pi. Just like that.
the line.
Wow.
Okay? So because it's the same, the ratio from the circumference to the diameter is the same for every circle. Okay? Because all circles are similar. So we name that
And
pi.
It makes sense because pi is as infinite as a circle is.
True.
Big brain.
Oh, pi isn't infinite. Pi has an infinite number of digits. But
Exactly.
pi isn't infinite.
Well, it's not. Yes, but its digits go on.
I would
forever.
qualify it as infinite.
Because it's infinitely increasing, but by an infinitesimal amount.
So,
But it's not
Yes, but that's like putting.
It's
an
not
unstoppable
increasing, it's
force
constant.
against an immovable object. It's basically the same.
that's my goal
They're
in
gonna
life, make
cancel
an
each other
infinite
out
pi.
automatically.
Like
it's not increasing, it's a
If you
constant.
go further
Yeah,
and further
yeah,
out trying to get closer.
I'm tired, dude.
Yes,
No, it
but
won't.
it's not possible because it's
It doesn't increase.
Well, pi itself doesn't, but our approximations of pi as you get more and more exact.
So I
Yes,
say
but so
pi
do
is
circles.
infinite, so.
So do circles,
move
therefore
on.
they are
I
also
say we go
infinite. No
golfing.
one can actually say.
Okay.
Yes.
Pi is
Anyway,
pi.
shh. How much larger is the circumference of circle B than the circumference of circle A?
Is pi equals pi.
Okay, the ratio between them isn't, but how much larger is the actual circumference? How did we do that when we were looking at the ratio of the circles themselves?
We
How did we do that when we were looking at the ratio of the circles themselves? Say it.
We divided.
Yeah, we divided. What did we divide by what?
We divided, well, for like square, we divided the bigger circle by the little circle.
Yeah, so all we have to do here is when we're looking for this, how much larger is it? We just need to we need to find the scale factor. So again, remember that circumference is equal to pi 2r, and we've got 2r1 and 2r2, so we're going to say the circumference of the larger circle is pi 2r2, the circumference of the smaller circle is pi 2r1. What happens when you divide something by itself, like pi and pi? Whoop, they cancel, they equal 1. What about 2 divided by 2? Whoop, what about r2 divided by r1? It's r2 over r1, so the how much larger is it is r2 over r1 larger. Is that scale factor the same as the radius that we found earlier? Yeah. Right? Awesome. Okay. Now, how about this one? Do we think that this is true or false? The area divided by the area is equal to the circumference divided by the circumference.
Yes.
Okay, let's prove it to ourselves. What is the area formula for a circle? Pi times r squared. So we've got pi r2 squared divided by pi r1 squared. And the circumference, we've got pi 2r1 and pi 2r2. So let's see if we can cancel those things out to be equal to one another. I'll rewrite it down here. Pi r2 squared divided by pi r1 squared is equal to pi 2r squared. Nope, pi 2r1, my bad. Divided by pi 2r2. Crap, I said that upside down. Pi 2r2 divided by pi 2r1. There we go. Whew! What a mouthful. Okay, on this left-hand side, what cancels out? Pi, whoop! So we've got r2 squared divided by r1 squared. And on the right-hand side, what cancels out?
pi and
Whoop! And 2, not the r though. So we've got r2 over r1. Dang, so they're the same, yeah?
Can you read?
No.
Are they? Let's just for kicks and giggles say that the radius of 2 is equal to 5. And the radius of 1 is equal to 2. Let's plug these in and see if they're the same. 5 squared over 2 squared equals 5 over 2. And I guess we could put a question mark there. What is 5 squared? 25. What is 2 squared?
4.
Yeah. Is that equal to 5 over 2?
Obviously.
Yes.
It's not equal.
If you were to divide 25 by 4, you would get 6.25. 6.25. If you were to divide 5 by 2, you would get 2.5. Those are not equal. So, r2 squared over r1 squared is not the same as r2 over r1. Okay, we can't cancel out squares. We cannot cancel those out like we did pi and like we did 2. So that means that the area, when we're multiplying an r times an r, that is not a proportion. Okay?
That's like a really good hurt. That's strangely good.
False.
Where?
Where it says no.
Yeah, you might want to fix your back before you go.
Where? Oh, I see it.
Yeah.
Yeah, that's really nice. All right, great. There we go. They are not the same. Cool.
We are not the same.
It is time for your homework. Remember, perpendicular bisectors. That is my hint to you. Okay, bye.